Hello. So, very good evening to all. Is it audible? So, today's topic is transmission line. Okay. So, in that one, what is the definition of transmission lines and what are the characteristics of transmission lines? Okay. So, that we will see in this topic. Okay. Okay. So, 4M9, 4M9.
Yes, sir.
Okay, ma. Is it visible the screen?
Yes, sir.
Okay. So first of all, so what is transmission line? Transmission line is nothing but it is a conductor designed to carry the electricity or an electrical signal over large distance with minimum losses and distortions. Okay, so it is a conductor design which carry the electricity or electrical signals over large distances with a minimum distortion or minimum losses. Okay, or in term, it's a very simple definition of a transmission line is a system of a conductor that transfers electrical signals from one place to the another place. Okay? That is the meaning of the transmission lines. Now, the main purpose of these transmission lines is the current flow in the transmission line induces the magnetic flux. When the current in the transmission line changes, the magnetic flux also varies due to which EMF induced in the circuit. Okay? So that is the meaning of these transmission lines. Next, now what are the different types of a transmission lines? Now there are different types of transmission lines. That is nothing but two-way transmission lines, coaxial cable, waveguides, microstrips, and optical fiber or fiber optics. Okay, two-way transmission lines or two-way balancer lines, then coaxial cables, then waveguides, microstrip, and fiber optics or optical fibers. Okay? Now, see, so the first introduction of this transmission line is a wave propagation in unbounded. Okay, so the wave is propagating in unbounded in free space, lossless dielectric, lossy dielectric, and conducting media used in radio or TV broadcasting. Okay, TV means that is the television broadcasting. Next. So the transmitting the power or information or energy is by guided structures. Guided structures will guide or direct the propagation of energy from source to the load. Now, while we need to transmitting the energy or power or information from the guided structures, guided means that is the connecting wires. Okay, from one place to the another place, that is from source to the destination. Okay, that is the transmission lines. The typical example of guided structures or transmission lines or and waveguides. Okay, so we can using any type of guided structures, that is two-way transmission line, waveguides, coaxial cable, microstrips, and optical fibers, depends on the type of applications. Yes, sir. The transmission lines are used at a frequency from DC to about 50 or 60 gigahertz of frequency. But anything above 5 megahertz only short runs are practicals. So the transmission lines are used at a frequency ranges from DC. DC means that is the 0 hertz frequency to 50 or 60 gigahertz of frequencies. Because the attenuation is increases dramatically dramatically as frequency increases. Okay, so while increasing the frequency, then the attenuation losses will increase dramatically. So only particular frequency only we can using these transmission lines. If more than that frequency, automatically the losses will increase. So there are three types of losses in conventional transmission lines. That is ohmic loss, dielectric loss, and radiation loss. Okay? These are the three losses will occurs while transmitting the high frequencies in a transmission lines. Next. An ideal transmission line consists of two parallel conductors of uniform cross-sectional area. Okay? The cross-sectional area of the two parallel conductors have the same. The conductors possess a capacitance per unit length is C and an inductance per unit length is L. So while this transmission line is a very large distance per unit length, what is the capacitance value? And per unit length, what is the inductance value? But these two parallel conductors have the same cross-sectional area. Okay? So the transmission lines are commonly used in power distributions and in communications. Okay? While transmitting the power, high power lines from one place to the other place, that is generating to the distribution lines. And in communication, you can using the two-way transmission lines for a landline telephone system. While connecting the landlines, it's like a BSNL landline phones. We are using the two-way transmission line connected between the exchange to the mobile, exchange to the phone, handset. Next. So these are the examples of transmission line. First one is parallel lines. Two parallel lines have the same cross-sectional areas. And second one is coaxial cables. Okay, coaxial cable. Its example is coaxial cable is dish wire, and wave. Third one is waveguides, and fourth one is a conductor on a plane, and fifth one is microstrip lines. So depends on the applications or depends on the operating frequency, the transmission lines may vary. Okay. So what are the parameters of a transmission lines? Now the transmission lines are, there are four parameters, that is resistance, inductance, capacitance and conductance G. So or LCG, these are the primary parameters. Okay. The transmission line parameters are resistance per unit length or inductance per unit length is L, capacitance per unit length is C. These parameters are uniformly distributed along the entire length of the line. So these parameters are uniformly distributed along the entire length of the lines. Uniformly distributed means the current passing through this entire length of the line is constant. Okay? So the magnitude and phase is same for the entire length of the transmission lines. So these parameters are called as a distributed or primary parameters. So already I told that these primary parameters of a transmission lines is or LC and one more parameter, that is conductance G. Okay. So by using these primary parameters of or LCG, then we can deriving the some other parameters, that is attenuation constant, phase constant, then propagation constant, characteristics impedance, Z0 value. So these are all parameters you can deriving based on these primary parameters. Then that parameter we can call it as a secondary parameters. So any other parameters derived in terms of these primary can be called as a secondary parameters. Okay. Then consider a coaxial cable connecting a generator or source to the load, as shown in that we will see in the next slide. When switch S is closed, then the inner conductor is made positive with respect to the outer one, so that the electric field is rapidly outward, as shown in figures 1b. According to Ampere's law, the H field is in circles. Now, see, here it is a transmission lines of coaxial cable. Now, the inner conductor is applying the, now here this inner conductor is given to the inner conductor is applying to the voltage V of G, and if S is closed, switch is S is closed, then the current is passing through this inner conductor. Okay? The S is closed, then the current passing through this inner conductor, then an electric field is produced in this coaxial cable. Then the load is connected at the secondary side, that is RL. Okay, so the source, the electrical signals will passing from generator to the load through coaxial cables. Now, while passing the current through this inner conductor of the coaxial cable, then the field must be produced in that coaxial cable like this. Now this continuous, this is the center conductor, inner conductor, this is the outer conductors. Just 1 minute. Next one made construct the system. Now, so the voltage is applied at the inner conductor of the primary side. When the switch is closed, this current is passing through this one, that is I value. Then the electric field is produced from this inner conductor to the outward conductors. Now, so this is the inner conductor, this is the outer conductors. Okay, the area of cross sections is this one. Now, these continuous lines representing the electric field and the dotted lines representing the H fields. Okay, so due to pointing vector P is equals to E cross H. Okay, so what is the need of pointing vector? The pointing vector is used to find the power delivered or power transmitted, average power or total power from the electric field and magnetic field. So due to the pointing vector, that is P is equals to E cross H along the transmission lines. Thus, closing the switch established a transverse electromagnetic, that is TEM. Now, generally, the trans TE waves, TM waves, and TEM waves. That is nothing but TE is nothing but transverse electric, and TM is transverse magnetic, and TEM, that is both transverse electromagnetic wave propagations along the lines. This wave is a non-uniform plane wave, and by means of its power is transmitted to the transmission lines. So this wave is a non-uniform, so it may change the magnitude and directions. So non-uniform, it is not a uniform plane waves. It uniform means it will be constant for the entire length. But in this here, it is a non-uniform plane waves. Okay. Next. So while we derive the equivalent circuit of these transmission lines is this one. Now see here, this is a one transmission line and this is another transmission lines. This transmission line equivalent circuit is representing in terms of the primary parameters, that is R, L. Resistance and capacitance are in the series combination, and this G and C are connected in parallel between these two wires, two parallel wires. Okay, so G and C are connected in parallel combination, and R and L are connected in series combination. Okay, so this is one component and this is another component. I'll doing the expressions now here also. So RLCG, RLCG like this. Then the total equivalent circuit of these transmission lines. From these transmission lines, then we can derive the expression that is called as a transmission line equation. Okay, So the input voltage is V of Z of t, then the resistance is R into del of Z, and inductance is L into del of Z, and conductance then G into del of Z, and capacitance is C into del of Z. Then the output is V of Z plus del of Z comma T, that is the load at this point. Okay, so this del of Z is nothing but it is a difference, minute values. Okay, now so by applying the Kirchhoff voltage law, then the output voltage Kirchhoff voltage, then the equivalent circuit V of Z comma T. So this voltage minus this voltage is equals to I into I of Z of t minus I of Z of del of t into R of Z plus L into this one dou by dou t of I of this value. Okay. Now, in terms of while applying the Kirchhoff current law, this current minus this current is equals to V of Z of t into this one parallel combination plus C into del of Z into dou by dou t of V of Z of t. Okay. Now by dividing the each equation by del of Z and taking limit del of Z tends to 0, then so taking the limits on both sides, first dividing this expression by del of Z. Okay, so del of Z and taking the limits. So what will happen? So this expression, so what is this expression? This is the general differentiation formula definitions. Okay, so this is the limit del of Z tends to 0 V of Z of t Z plus del of Z minus V of Z of t divided by del of Z. This is the general expression for the differentiation. Therefore, dou V of Z of t divided by dou of Z. Okay, so is equals to this I of t into R minus L into dou by dou t. Similarly, this expression also can apply limits value, then it will comes rate of change of current dou I of Z of t by dou Z is equals to V of Z of t into G minus C into this one. Now, while considering these particular cases of, now here, if the transmission line is a lossless, so if the transmission line is lossless, then R is equals to Z is equals to 0. Therefore, dou I of Z of t by dou Z is equals to, so here in this equation this term is equals to 0. So only dou V by dou Z is equals to minus L into this one. And in the second equation this Z is G is equals to 0. That is dou I by dou Z is equals to minus C into dou V by dou T. Okay. So all of you note down this expression while I am explaining. Next. Therefore, V of Z of t is equals to real part of V of Z into e power j omega t. Similarly, current is equals to real part of I of Z into e power j omega t. Okay. Now, here, if for a sinusoidal steady state conditions, So previous case is if it is a time varying field. Now here it is a steady state. So already we discussed in the Maxwell equations for time varying fields and static fields and time varying field in free space mediums. Okay. So in the steady state condition, there is no rate of changes of the variable rate of changes of the component is equals to zero. It is a constant values. There is no changes. Okay, so that's why we can take consider only the real part. So V of Z is equals to real part of V of Z into e power j omega t, and I of Z is equals to real part of this one. Okay, so while taking the differentiation, dou V by dou t is equals to dou real part. Similarly, dou I by dou t is equals to real part of j omega into I of Z. Okay, next. Now see here, this j omega is here you can differentiate it with respect to t, then v of z is constant, so you can take real part of v of z into dou e power j omega t by dou t. So e power j omega e power x differentiation is e power x into x coefficient. So here you can differentiate it with respect to t. So e power j omega t, e power j omega t, t coefficient is j omega. So j omega into v of z into e power this one. Similarly for the current also, it will come the same. Okay? Real part of j omega I of z into e power j omega t. Next. So is it audible, man? Hello? Okay, okay. Just I am highlighting all the important points. Next. Now, the same expression. Now, dou v by dou of z is equals to minus r plus j omega into I of z, and dou I of by dou z is equals to minus r g plus j omega c into v of z. So this expression we can using in telegraph equations. Okay, this expression we can using in telegraph. This one. Now, while differentiating the expression dou square v by dou z square is equals to minus gamma square into v of z. Similarly, the second expression dou square I by dou z square minus some gamma square into I of z is equals to 0, where gamma is equals to, I can write it here. Gamma is equals to I plus j beta, that is equals to r plus j omega l into g plus j omega c per meters. Okay, where gamma is nothing but propagation constant, and alpha is a, so that gamma is can representing in terms of both real and imaginary part, that is alpha plus j beta. Okay, so where alpha is a attenuation constant and beta is a phase constant. Okay, now here this propagation constant gamma is equals to in terms of primary parameters or LCG. Okay, this gamma is a secondary parameters, whereas or LCG are the primary parameters of a transmission line. Okay. Now, so in terms of now, while dividing this expression V of Z by I of Z, this V of Z voltage and current can be written in terms of exponential forms. Exponential form, that is the expression, this one. Okay. Now this voltage by current we can getting the impedances. So V naught by I naught or minus V naught by I naught minus, that is equals to square root of R plus j omega L whole divided by G plus j omega C. Okay, that is the voltage is equals to R plus j omega L and current is G plus j omega C under square root of, that is equals to Z naught. This Z naught is the characteristics impedance. So here the Z naught is a secondary parameter of a transmission line. This secondary is also defining in terms of primary. R plus j omega L divided by G plus j omega C. J omega is a frequency component, that is omega is equals to 2 pi f. Then R, L, C, G are the primary parameters. Therefore, gamma, that is the propagation constant, and characteristics impedance are called transmission line parameters. Transmission line secondary parameters, because transmission lines has both the primary as well as secondary. Next. Now, so this is the simple expression, general expressions of a transmission lines. Okay. Now, if the transmission lines is whether it is a lossless transmission line or lossy transmission lines. Okay. Now, if the transmission line is a lossless means the resistance R and G component is equals to 0. Okay, now substituting this R is equals to 0 and G is equals to 0 in the previous expressions of propagation constant and characteristics impedance. Then the modified expressions or gamma is equals to alpha plus j beta. Then alpha plus j beta is equals to what in the previous expression? Square root of R plus j omega G j omega C. So R is 0, G is equals to 0. So j omega into J omega C. Now only multiplying J square omega square C. Okay. Then it will comes J omega whole square. Now you can take from the square root come out. Then it will J omega into square root of LC. Okay. Now here while comparing this real part and imaginary part, here alpha is equals to 0 and beta is equals to omega into root LC. Okay, so there is no real part, only propagation constant. There is no attenuation constant. Okay, similarly, characteristics impedance here. So R is equals to 0, G is equals to 0. So it will comes only square root of J omega L by J omega C. So J omega cancel. So it will comes only square root of L by C. So this is the square root of L by C. Okay. And note down these points. So while doing the problems, you can use these formulas. So what is attenuation constant? What is propagation constant? What is phase constant? What is the characteristics impedance of a two-way transmission lines for a lossless medium or a lossy medium? Okay. Next. Now, so we can conclude this lossless lines equation or lossless transmission line equation. The propagation constant alpha is gamma is equals to alpha plus j beta. So in that one, the attenuation constant alpha is equals to 0 and beta is equals to, it will comes omega into root LC because of R and G component is equals to 0. Then phase velocity, already seen in the last class, that phase velocity is equals to omega divided by k. K is nothing but the phase number. Okay, so here it is, you can using omega by beta, where beta is equals to omega into root LC. Okay, so while substituting this expression here, then it will comes, so omega divided by beta, beta is equals to omega root LC, so omega cancel, so it will comes 1 by root LC. Okay, the same expression I can write down here, so V is equals to 1 by root LC. Whereas wavelength lambda is equals to 2 pi by beta. Then a reflection coefficient at the load delta is equals to ZL minus Z0 divided by ZL plus Z0. Okay, this reflection coefficient is less than 1. Okay, now it will lies between 0 to 1. Okay, suppose if the load impedance is equals to the characteristics impedance, that is ZL is equals to Z0, then what will happen here? So if the load impedance is equals to the characteristics impedance, then this delta is equals to 0. Okay, if it is not equal, this value is less than 1, because of in the denominator it will be additions z. Okay, in the numerator subtraction, so denominator is in the addition, so the total resultant value is less than 1. That's why the reflection coefficient is lies between 0 to 1. Okay, next, from this reflection coefficient, the voltage standing wave ratio VSWR is equals to 1 plus delta naught divided by 1 minus delta naught. Okay, where delta naught is reflection coefficient. So reflection coefficient is lies between 0 to 1. Okay, suppose if delta reflection coefficient is equals to 0, So what about this VSWR? So what about this VSWR? If delta naught is equals to 0, 1 plus 0 divided by 1 minus 0. So it is equals to 1, lower limit. If the upper limit delta naught is equals to 1, so 1 plus 1 divided by 1 minus 1. So 2 divided by 0. 1 minus 1 is 0. So anything by 0 is infinity. So the VSWR is lies between 1 to infinity. Okay. So the reflection coefficient of a transmission lines is lies between from 0 to 1, whereas in VSWR lies between 1 to infinity. Okay, so the reflection coefficient at any position of a transmission line, this one is we can calculating at the load side. Okay, suppose because the transmission is a far length, long distance, so at any point in between the source and destination. So the delta in is equals to delta naught into e power minus 2 gamma into d, where d is distance and gamma is in this one propagation constant alpha plus z beta. Okay. Similarly, for the input impedance, this is equals to these definitions are only for the lossless. Okay. So I can write down this one. Once completed, you can tell me. I'll go for next slide. Is it audible? Hello? So completed. So completed.
Yes, sir.
Okay. Next, distortion-less transmission lines. So for distortion-less transmission lines, the condition is R by L is equals to G by C, or R by G is equals to L by C. Okay, that is the condition. Now you can substituting this condition in the previous expressions. So a distortion lines is one in which the attenuation constant alpha is frequency independent, while the phase constant beta is linearly dependent on frequencies. Okay, so that is the condition. So any transmission line, it can satisfy this condition. R by L is equals to G by C, or R by G is equals to L by C, both are same. Okay, R by L is equals to G by C, or you can take G is comes to this side. Okay, G you can take this side, and L is you can take this side. So R by G is equals to L by C. Resistance, conductance, impedances, capacitances. Now you can substitute this condition in the previous expressions, like here. Here, when general expression is this one, gamma is equals to alpha plus j beta, that is equals to R plus j omega L into G plus j omega C. Similarly, characteristics impedance. Now you can substitute in this condition in that expression. Now it will comes gamma is equals to this one. In this first expression, R plus j omega L into G plus j omega C. Now you can take R is common in the first term, that is R common. Take R common. So 1 plus j omega L by L. In second term, G is common. Okay. Now what will happen? Square root of RG into 1 plus j omega. So R by L is equals to, so from this one, so L by R is equals to, you can given this expression, that is C by G. Okay, here. So 1 plus j omega C by G into 1 plus j omega C whole square. Square root it cancels. So it will comes square root of RG into 1 plus j omega C by G. Now this can written in general form alpha plus j beta. Okay, therefore alpha is equals to this one. Okay, constant value, and j beta, j term is this one. So you can comparing both the real part and imaginary part. I will erase all these things. Okay, therefore R is equals to square root of Rg, and beta is equals to omega into square root of Lc. Okay, Lc means you can multiply this factor, square root of Rg into 1, square of Rg plus j omega into square root of Rg into C by G. Okay. C by G is, again you can write down R by L. So R cancels, then it will comes root LC. Okay. Then phase velocity is equals to omega by beta. Beta is equals to what? This one. Omega into root LC. Now you can substitute beta is equals to omega root LC. So omega cancel, then it will comes 1 by root LC. Then impedance, characteristics impedance Z naught is equals to what? Square root of R plus j omega L divided by G plus j omega C. Okay, same thing you can write, take the common of R and G in the numerator and denominator. See here. Okay. R plus j omega L divided by G plus omega. So then you can take R is common, then 1 plus j omega L by R. In the denominator, G common, so 1 plus j omega C by G. Now you can substitute L by R is equals to C by G. So it will comes only R and G terms. R and G terms. R by G or L by C. You can write in any expressions. Okay. So see the difference of lossless and distortionless. In the lossless, the resistive component is zero. That is R, and conductive component is zero. R and G component is zero. Whereas in distortion, that phase constant and attenuation constant are independent of frequency. Alpha is independent of frequency. That's why I see here in the alpha is equals to only R and G. There is no frequency dependent component of L and C component. Whereas beta is dependent on frequency because beta is equals to omega. Omega is equals to 2 pi f. So f is the frequency and L J omega L C J omega C. Okay, it is a frequency dependent component. So you can write down. Okay, completed. Next. Now you can conclude this lossy compression, lossy transmission line, that is general transmission lines, distortionless and lossless. Okay. So first, the propagation constant gamma is equals to square root of R plus j omega L into d plus j omega C. In the lossless, R is equals to G is equals to 0. So it will comes j omega into square root of LC. Okay, this one. Whereas distortionless, R by L is equals to G by C. So it will come square root of RG plus j omega into root LC. Now, characteristics impedance Z0 is equals to, in general expression, that is lossy, R plus j omega divided by G plus j omega C and the square root. Okay. In the lossless, R is equals to 0, G is equals to 0. So it will comes j omega L by j omega C, j omega cancel, it will come square root of L by C. Okay. And in distortionless also same thing. Okay. R by L is equals to G by C, it will cancel. So it will comes only square root of L by C. Next. Phase velocity U is equals to omega by beta. Okay. Similarly, phase velocity for lossless omega by beta. Beta is equals to what? Here omega into root LC. So omega omega cancel. It will come as 1 by root LC. Okay. Here also same thing. Then lambda is equals to 2 pi by beta in the general expression, and the losses also 2 pi by beta, and the distortion-less also 2 pi by beta. Okay. So this is the topics we discussed in today's. Next. So any doubts in this one? Any doubts? Any doubts? Hello? Is it audible?
Yes, sir.
Okay. Any doubts? So while doing the problems, you can use these expressions directly. Okay. So once again, I can conclude, revise these today topics. So transmission lines, the transmission lines is nothing but it can carry the information or electrical signals or power from source to the destination. If it is a electrical lines, then it will taking the power from the generating station to the household purposes, that is distributions. Okay, if it is a in terms of communication, it will transmitting the voice signals or data signals. Okay, data is can be defined classified into, that is text data, image data, audio data, and video data. Okay, these data can be transmitting from source to the destination. Okay, through a cables. That cable is nothing but a, we can call it as a transmission lines. The transmission lines can be classified into different categories like two-way transmission lines. Example is landline telephone. Okay, coaxial cables like a dish wire. Example is a dish wire. That is in dish wire. It will consist of two conductors, inner conductor and outer conductors. These inner and outer conductors are separated by the insulators. Okay, waveguides, microstrip lines, and optical fibers. Okay, so based on the applications, we can using different types of transmission lines. In all the transmission lines, it will carry the information at a different speeds. Okay, in two-way transmission line, the data speed is in kilobits per seconds. In optical fiber and microwaves, the data speed is in Mbps, megabits per seconds. So based on the application, you can using these type of the transmission lines. Now the equivalent circuit of these transmission lines are represented by the primary components of the transmission lines, that is R, L, C and G component, that is resistor, inductor, capacitor and conductance. Okay, resistor and resistors and inductors are connected in series combination along the line, and conductance and capacitance are connected in the parallel combination. Okay, now from these or LCG are called as a primary parameters of a transmission lines. By using these primary parameters of a transmission line, Okay, deriving the some other parameters. Okay, that parameters you can call it as a secondary parameters of a transmission lines. Now, from this equivalent circuit, by applying the Kirchhoff voltage law and Kirchhoff current law, you can getting the voltage and currents in terms of RLCG components. Okay? From that RLCG component, then can defining the propagation constant gamma is equals to square root of R plus j omega L into G plus j omega C. Okay, that can be defining in the general expressions of a real part and the imaginary part like alpha plus j beta. Okay, where alpha is a attenuation constant and beta is a phase constant. Okay, now then another definition of these transmission lines is characteristics impedance Z naught. So Z naught is equals to square root of R plus j omega L divided by G plus j omega C. Okay. So these are the expressions for general expressions or lossy transmission lines. Next, if the transmission line is considered as a lossless, then simply you can substitute a resistance and a conductance R is equals to G is equals to 0. So you can substitute R is equals to G is equals to 0. Then that gamma is equals to, it will come solely J omega into root LC and the Z is equals to simply square root of L by C. Okay, and similarly you can defining the phase constant and lambda value also. That is the wavelength. Now, if it is a transmission line is a distortion-less transmission line, then the condition is R by L is equals to G by C or R by G is equals to L by C. Okay. Now, distortion-less transmission line is nothing but the attenuation constant is independent of frequency and phase constant is dependent on frequency. So the condition is R by L is equals to G by C. Okay. So while substituting this condition, then the phase constant, the propagation constant, gamma and Z naught value can define. Along with secondary parameters of gamma and Z can defining the reflection coefficient delta naught is equals to ZL minus Z naught divided by ZL plus Z naught. So the value of the ranges of reflection coefficient is less between 0 to 1. Whereas in standing wave ratio is equals to 1 minus reflection coefficient divided by 1 plus reflection coefficient. So the ranges of the standing wave ratio is lies between from 1 to infinity. Okay. So this is the conclusion of today's class. So any doubts? Any
Sir,
doubts? Tell
sir,
me.
first 3 slides చూపిస్తారా సార్ ఒకసారి?
First slide.
ఎస్ సార్,
Okay.
నెట్వర్క్ ఇష్యూ వల్ల జాయిన్ అవ్వలేదు.
Okay. This one. This is the first slide. This is the first slide.
ఓకే సార్.
Shall I go for next slide?
ఎస్ సార్.
Which is different types of transmission lines. That is parallel lines. It is like a landline cable line, landline telephone wire, and this is a coaxial cable. Example is dish wire while connecting from the antenna to the TV, and waveguides, microstrip lines. Shall I go for next slide?
Yes, sir.
Okay. This is third one. That is primary parameters and secondary parameters.
Okay, sir.
This is next slide.
Yes, sir. ఇక్కడ నుండి విన్నాను సార్.
Okay. So any
థ్యాంక్ యూ
other
సార్.
doubts? Any other doubts? So I will stop the presentation. Any doubts? Others? Okay, ma. Thank you.